Welcome to the conceptual chemistry class at Lake Mills High School in Lake Mills, Iowa. Throughout the course of the year, you will be watching a series of videos as part of our flipped classroom model to help you in your journey to learning some chemistry. Our first unit of the year is on atomic structure and nuclear decay. Our first lesson for our atomic structure and nuclear decay video is on basic atomic structure. At the beginning of each lesson, we will take a look at the learning standards and targets that we are working on for the lesson. For this particular video, we are working on the essential standard for the unit of applying my knowledge and understanding of the composition and structure of atoms. Within that, we have several learning targets that you can see here. And for this first video, we'll be working on these first two, specifically the first learning target here, a little bit of the second. But we'll just jump right into this first one. We want to be able to identify and describe the subatomic particles. So notice at the top of the slide here you see that learning target, and that will always be the case where on each slide you will see the learning target we're working on, which will allow you to more quickly navigate the videos if you're looking for something specific, or if you're looking at your PowerPoint slides, if you're looking at those that you've printed out, or perhaps you're looking at them online, you can quickly find the slides that you're looking for. So let's talk about atoms. There are atoms absolutely everywhere because our entire universe is composed of atoms. An atom, if you want a definition, it's simply the smallest particle of an element. You might be wondering, well, what is an element? Where would I find a list of elements? Well, that's this thing right here. That's our periodic table. We have roughly 120 known elements. It's at 118 more specifically. You can see the last one here. Every one of these elements, the smallest particle of all of those, we would call an atom of that particle. So an atom of hydrogen, or an atom of helium, or lithium, or beryllium, etc. So every element is made up of atoms. And these atoms, for each different element, they are unique. In other words, a hydrogen atom, would not be like a helium atom, which would be different from an oxygen atom, which would be different from a gold atom. Our goal over the next few lessons is to explore what it is that would be different about those atoms. So let's take a look at the structure of an atom. When we talk about structure, really we're talking about two things. A, what something's made of, and B, how those different things are put together. So any atom is composed of three subatomic particles. Now the word subatomic really tells us what it is that we're talking about here. The prefix sub means smaller than or within, and then atomic referring to atoms. So we're talking about three particles that are smaller than the atom. So the atom, while it is the smallest particle of an element, it is not the smallest particle, because we can divide atoms into these smaller subatomic particles. Those subatomic particles, you've probably heard of them before, are protons, neutrons, and electrons. And then as far as the structure, how those subatomic particles come together to form an atom, it looks something like this. And I say it looks like this, this is not an actual picture of an atom, of course. This is simply a model of an atom. And when we say model, we don't necessarily mean something we build in 3 dimensions. It's just a way of thinking about it. So when we think about an atom, it's most useful to think about it in a way that you see in this picture here, where we have protons and neutrons. They're in the center of an atom, and they make up what's called the nucleus of the atom. So these protons and neutrons go in the nucleus, in the center of the atom, and that nucleus is really, 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 really tiny. This picture doesn't do it justice. A nucleus of an atom is incredibly tiny. Those particles are packed in really, really close. And then the electrons are outside the nucleus. Now this particular model, and this is very common in pictures of models of atoms, show the electrons as going around the nucleus in a circle. We know now that electrons don't actually orbit the nucleus like, say, the Earth orbits the Sun. But it is a useful image, though, because it does express the idea that the electrons that we see here are outside of the nucleus, and the protons and neutrons are inside the nucleus. So a few things about each of these subatomic particles. Protons, and we can see this in the picture, they are positively charged. Notice the plus sign there, those yellow particles there are the protons. They are positively charged. They have a 1+ charge. Their mass is roughly 1 atomic mass unit, or AMU. The atomic mass unit, all you really need to understand about that is it's a really tiny unit of mass, but it's about 1 AMU is the mass of a proton. You'll see that the other particle in the nucleus is the neutron, and neutrons, you can see over here, these are the orange particles. Those are neutrally charged, thus the name neutron. They have no charge, so there is 0 charge in a neutron. And their mass is also right about 1 atomic mass unit, 1 AMU. So a proton and a neutron, they're right about the same mass. They're not exactly the same mass. A neutron is actually slightly heavier. But for our purposes for now, we can just say they both have a mass of about 1 AMU. And then finally we have electrons, and we can see those are not in the nucleus. They're outside the nucleus. Electrons are negatively charged, a 1 minus charge. So even though electrons, as we'll see here in just a bit, are way less massive than protons, their charge of 1 minus is exactly opposite the charge of a proton of 1 plus. So if I had, say, 4 protons and 4 electrons, their charges would perfectly cancel because the charge on a proton is exactly opposite the charge on an electron. The mass of an electron is way smaller than 1 AMUs. So an electron has very little mass compared to either a proton or a neutron. So even though 1 atomic mass unit is a really tiny mass, electrons are way smaller than even 1 AMU. In fact, it would take something like something close to 2,000 electrons to equal the mass of a single proton or neutron. That's how tiny electrons are. So a few review questions here. As these questions come up, read the question, pause the video, answer it yourself, and then play the video and see how closely your answer matches mine. So question number 1, which elements are made of atoms? All elements are composed of atoms. There's no such thing as a single element that is not made of atoms. Question number 2, what are the 3 subatomic particles that compose atoms? Those subatomic particles are protons, neutrons, and electrons. Question number 3. Where is the nucleus in the atom, and which particle or particles is in it, or are in it? Well, the nucleus is found in the center of an atom, and the nucleus is composed of protons and neutrons. Where is the majority of an atom's mass located? Explain. Now, this was not addressed specifically in the previous 2 slides, but based on what we learned about the masses, we should be able to say that nearly all of an atom's mass is located in the nucleus. This is because the particles that are in that nucleus, the protons and neutrons, are much heavier than electrons, which are not in the nucleus. In fact, if you were to think of it as a percentage terms, well over 99% of an atom's mass is found in an atom's nucleus, and that's for any element. It does not matter which element we're talking about. Well over 99% of the mass is found in that nucleus. Last question, does the nucleus have an overall charge? Again, not specifically addressed in the previous slide, but based on what we learned about the charge of the particles and what particles are in the nucleus, we can say yes, the nucleus does in fact have an overall charge. This is because the nucleus contains protons, which are positively charged, and so the nucleus as a whole is positively charged. So looking back at our learning standards and targets here, we have addressed this first learning target, identify and describe the subatomic particles. Now we're going to take a look at this second learning target. Now we're not going to look at all of these terms, define and apply the terms atomic number, mass number, etc. The only one we'll focus on here in this lesson is on atomic number. The next terms there we will hit up in the next lesson. So what we want to understand is that for every different element, there's going to be a different atom. There's no such thing as 2 identical atoms of different elements. So the question is how is an atom of one element different from an atom of another element? And here's the big idea. And if you're really to remember just one thing from this entire video, it would be this right here. Atoms of different elements, they have to have a different number of protons. There's no such thing as 2 atoms, if they're different elements, having the same number of protons. That does not exist. This is because of the element's atomic number. The atomic number for an element is simply the number of protons that are in the nucleus of the atom. Every element has a different atomic number. In fact, that's how they're ordered on the periodic table. If you look at your periodic table, you will see boxes that look something like this. I just chose two here, nitrogen and oxygen. Now your periodic table might not look exactly like you see here in front of you, but any periodic table is going to contain this same basic information, where we have the symbol for the element. In this case, nitrogen is capital N. We see the name here, and then that whole number 7, and maybe it's here in the center. On this periodic table you see, maybe on yours it might be somewhere else. That is the atomic number. So the atomic number of nitrogen is 7, that of oxygen is 8. These other two numbers you see here at the bottom, these are the atomic masses of the element. For now, that is not of our concern. We're just focusing on the atomic number. So here's what this tells us. Because the atomic number of nitrogen is 7, every single nitrogen atom has 7 protons. That's what defines it as nitrogen. If you have an atom and it has 7 protons, it's nitrogen. There's no such thing as a nitrogen atom that doesn't have 7 protons. Likewise, all oxygen atoms have 8 protons. If you have an oxygen atom, it has to have 8 protons because that is the atomic number of oxygen. So again, some review questions. Again, pause the video once you read the question, answer it yourself, and then play the video. Question number 1. What determines the identity of an element? So the identity of an element is determined by its atomic number, thus the number of protons, because every element has a unique atomic number. How many protons are in a magnesium atom? So looking at your periodic table, if you find magnesium, you'll see that the atomic number of magnesium is 12, and thus any magnesium atom will have 12 protons. Question 3. There are no copper atoms with 31 protons. Explain why this is. If you look at your periodic table, you will see the atomic number of copper is 29. Thus, if you have a copper atom, it has to have 29 protons. There would be no such thing as any copper atom without 29 protons. This is because the atomic number, it defines the element. So if we did have an atom with 31 protons, looking at your periodic table, you would see that would be a gallium atom, because gallium is atomic number 31. So going back to our learning standards and targets here, we're working on the essential standard of being able to apply knowledge and understanding of the composition and structure of atoms. And we hit up this first learning target, identifying and describing subatomic particles. And we started this second learning target here looking at the term atomic number. Our next lesson we'll look at these next terms: mass number, isotope, valence electrons. We'll also take a look at, really in some ways, all the rest of these learning targets in the next lesson.